new stuff? I think just the weekly assignment, and that's already been due, isn't it? So you don't have any homework, I don't think, right now. Okay. But I'm going to give you so much today. Just kidding. Okay. So one thing I want to say, this is kind of what we've been doing in lab, but I want to do it in class too, get it in your class notes. I want to talk about an intuitive understanding of acceleration in 2D. To talk about this, I first want to talk about what's going on with 1D. So I'll start with 1D. In 1D, acceleration just means that an object is what? What can acceleration do to an object in 1D? It can only make it speed up or slow down. That's all that can happen in 1D. Remember, 1D is moving along a line. So in 1D, acceleration makes an object speed up or slow down. If the object is speeding up, then the velocity and the acceleration have to be in the same direction. And if an object is slowing down, velocity and acceleration have to be in opposite directions. So for example, say that you have an object rolling along this path. And let's say that the object is moving up the ramp and slowing down. What are the directions of the velocity and the acceleration? Well, the velocity is in the direction of motion. So if it's moving up the ramp, then the velocity has to be like this. And if it's slowing down, the acceleration has to be in the opposite direction of the velocity. So the acceleration has to be like this. Okay, in 2D, acceleration means, it can mean two different things. One of those things is speeding up or slowing down. It means speed change. But what's the second thing that it can mean in 2D? What? Yeah, turning, exactly. And so what we have here is speeding up or slowing down is caused by a part of the acceleration that's parallel to the velocity. That's the one I call aparallel. And that works exactly like acceleration works in one dimension. Okay? So this is like one-dimensional acceleration. Turning is caused by a part of the acceleration that's perpendicular to the velocity. And this is a new thing. This doesn't exist in 1D. And so here are a set of steps for visualizing acceleration in 2D. So first, draw the object and its path in the real world. Okay, so none of this stuff happens in position versus time graphs. In fact, in 2D, we don't have position versus time graphs anymore. You could come up with ways to do it, but we're not going to. Second, draw the velocity vector, and that has to be tangent to the path in the direction of motion. Now, third, the question is it speeding up or slowing down? Let me word it like that. So, is it speeding up or slowing down? If the speed isn't changing at all, then you can forget about this step 3. There's no part of the acceleration that's parallel to the velocity. If it's speeding up, then which way is A parallel going to be? In the same direction as the velocity or the opposite?
Same.
Yep. So if it's speeding up, draw A parallel in the same direction as the velocity vector. And if it's slowing down, draw A parallel in the opposite direction of the velocity vector. Now for step 4, ask yourself, is it turning? If the path is curved, because that's what it means for the thing to be turning, fit a circle to the curve, and then A perpendicular points towards the center of the circle. And then the last step is the total acceleration is the sum of these two parts. Now, we know the directions of these two parts. So if both of these are non-zero, all we can do is give a range of directions for the answer. If one of these is 0, then we know the direction of the total acceleration is just the direction of the other part, okay? If both of them are 0, we know the acceleration is 0, okay? So let's do a couple examples and do this. This is the stuff that we did in lab last week. So first, let's say an object moves horizontally to the left with a constant speed. Okay, so the object's path is this way. There's the object. It's moving to the left. So the velocity vector is like this. Is the speed changing? No. So we don't draw any A parallel. Is it turning? No. And so we don't draw any A perpendicular, and so the acceleration vector is 0. Okay. Second, let's say an object is moving around a path like this. And it's moving with a constant speed. So what can we say about the acceleration here? Well, the velocity is tangent to the path in the direction of motion. So this is the velocity vector. Is the speed changing?
No.
No, it's a constant speed, so I'm not going to draw any A parallel. Is it turning?
Yeah.
Okay, it is turning. So we're either going to have a vector A perpendicular that's like basically straight up or straight down. Which one do we want here? Up, because you fit a circle to this, and toward the center would be up. And so our A perpendicular is perpendicular to the velocity like this. And so now we have this A perpendicular but no A parallel. So what's the direction of the total acceleration?
Between V and A, right?
Nope, not between V and A, because what we're doing is just adding the two parts of the acceleration. Okay, so V doesn't come into it at all. So all we do here is, well, you know, look at this equation. This A parallel is 0. So the total acceleration is just equal to that A perpendicular. Does that make sense? And so we'll just say that the total acceleration is just this. Okay? Okay, so now let's say a toy car speeds up as it rolls down a ramp. So it's going this way. I'm going to draw the path of the car like this. It's rolling down the ramp, so the velocity vector is this. Is it speeding up or slowing down?
Speeding up.
Yeah, speeding up. So A parallel is in the same direction as the velocity. Is it turning?
No.
No, so there's no A perpendicular. And so what's the direction of the total acceleration?
A parallel.
It's just equal to A parallel, yep. So it's down the ramp. And you can see that this is just when it's not turning, we've reduced this problem to a one-dimensional problem, and it behaves exactly like a one-dimensional problem. We just call this a parallel now. Okay?
I have still a question about the previous one.
Mhm.
Actually, not fully understanding. Since it is a constant speed, is that why A is not?
Yeah, since it's a constant speed, there's no a parallel. There's only an a parallel if it's changing speed.
Oh,
And so that's why there's no a parallel. And then because of that, since there's no a parallel here, the total acceleration is just equal to the part that's non-zero. Yep. And then the last example is like the deluxe model. So let's say we have an object in projectile motion traveling along a path like this. The velocity vector is tangent to the path in the direction of motion. Is this on its way up or on the way down?
down.
Down. So is it speeding up or slowing down?
Speeding up.
Okay, speeding up. So is A parallel in the same or opposite direction of V?
Same.
Same, yep. So there's A parallel. And now which perpendicular direction does A perpendicular act? Is it kind of up or kind of down? So if you fit a circle to this curve, its center would be on this side. So it's going to be perpendicular to those other two in this direction. And now we're adding the green and blue vectors together. We don't know what their magnitudes are. So all we can say is that the total acceleration is going to be somewhere in this direction. Well, we know that in projectile motion, the acceleration is down. So down needs to fall within this range, and you can see that it does. Okay, so that's the end of what we're talking about with 2D particle kinematics. And now we're going to get into 2D particle kinetics. So the next topic is 2D particle kinetics. And two of these words mean the same thing they did before. So 2D means motion in a plane. Particle, who remembers what particle means? This has already been a quiz question, and I'm sure it's gonna be a quiz question again at some point. So remember these, and it's free points. What's a particle?
It has mass, but it doesn't have a certain.
Yes, exactly. So we're treating, so one thing to remember is it's a mathematical treatment of objects, so it's not like actual objects have these characteristics, but it's a treatment of an object as having mass, but no size, no length dimensions. And then the new word here is kinetics. What we were doing before was kinematics, the slightly longer word. Now we're going to the shorter word, and we're basically just upping the complexity a little bit. So kinetics is kinematics plus the causes of the motion. And those causes are mass, force, later it'll be energy. Okay, so we haven't dealt with this stuff yet, but now we're starting to. And so before we can get into calculations, I have to define mass and force. And I'm going to start with the relatively simpler one, mass. Okay, so mass. The first thing that you have to remember about mass is, okay, this is a disservice that the bathroom scale, big bathroom scale conglomerates have, this is harm they've done to your understanding of things. Mass and weight are not the same thing. Your scale has a setting on it that lets you switch between kilograms and pounds. But pounds is measuring how much force you're applying to the scale, sort of indirectly measuring how much force gravity applies to you. Kilograms is a measure of mass, a totally different thing, although they're related through some simple mathematical equations, you know, but so just remember mass and weight are not the same. Weight is the force gravity applies to an object. And pounds are a unit for weight, not for mass. Okay. So what is mass? Mass is a measure of an object's resistance to acceleration. Okay? If it's easy to accelerate an object, it has low mass, and if it's hard to accelerate an object, it has high mass. Think of this football game moment. Okay. Okay, so here's one football player. Is a good exercise regime. And he's colliding with this football player. Yeah, it's a bad, this play isn't going to go well at all. Okay, so what's going to happen when those two collide? The big guy is going to have a very small acceleration from this collision. Okay. In fact, if he has his eyes closed when this collision happens, he might not even notice that they collide. You know what I mean? he's going to just basically keep running in the same direction at the same speed he was going before. The little guy, unfortunately, is going to very abruptly have his velocity changed drastically. He's going to go from having a velocity that points to the left to very quickly having a large velocity pointing to the right. Okay? So this collision is going to cause a small acceleration to this guy and a large acceleration to this guy. And so using the definition of mass, that tells you that this guy on the left has a big mass, and this guy on the right has a small mass. Okay? And in fact, there is a relationship a simple relationship between your weight, the force that gravity applies to you, and your mass. That's not surprising, even though they're not the same thing. But people only have weight if there's gravity. Okay, so on Earth we have weight, on planets we have weight, but if you're far out in space, you don't have any weight because there's no gravity. And even if you're close enough to the Earth that there's weight, but you're in orbit around the Earth, like in the space, International Space Station or something, there's no apparent weight because, well, basically you're in free fall as you travel around the Earth. So there's no way to measure your weight by using like an equivalent of a bathroom scale. And for people on the International Space Station, keeping track of their mass is very important because it's really easy to lose mass, muscle mass, and bone density. And they're working really hard to avoid that stuff happening. So it's very important to be able to measure their mass, but they've lost really the way that we're used to getting a measure of our mass. So what do they do to measure astronauts' mass? I've never seen the machine they use, but apparently they get in a thing that really quickly applies known forces to the person, and then they measure the accelerations that the person undergoes due to these forces being applied. And if these accelerations are relatively big, then this person has a small mass according to that. And if they're relatively small, then they have a big mass. The units, well, we're going to just say mass is one of the fundamental units. And so I'm just going to tell you that the SI units for mass are kilograms. You might think it's funny that the SI unit has a prefix like kilo on it, but that's just how it is. So it's not grams, it's kilograms. Yes?
I just have a question. If mass is measured by object's resistance to acceleration, wouldn't the big guy then have more acceleration than the small sticky guy? Because wouldn't he be more resistant to?
Yeah, he's more resistant to acceleration, so if you apply the same force to him, he accelerates less. The bigger the mass, the less the acceleration for the same force. Can you think of acceleration? Acceleration is how quickly you can change velocity, right? How quickly you change velocity.
Yeah.
So if you swing your hand at a flying bug, does its acceleration change a lot or a little? Does its velocity change a lot or a little? If you hit a bug with your hand?
I think a lot.
A lot, yeah. I mean, I guess I didn't give you anything to compare it to. Now imagine doing it to a semi-truck,
It's nothing.
Basically zero,
It's like that.
And so the bigger it is, the less the acceleration.
Gotcha.
Okay. This is also a reason why, you don't want to get in a car accident with a sedan where the other thing you run into is a semi-truck. It's the same problem as this. The semi-truck is going to have very little acceleration. The sedan is going to have a very large acceleration. Now, one thing I want you to remember, notice, mass is just a positive number. It doesn't have any direction. So it's not a vector because it doesn't have any direction. Okay, so now that's pretty much all we have to say about mass, and now we're going to talk about what force is. And force is a vector. That measures the intensity and the direction of a push or a pull. Okay, so this one is a vector. That's because it has a direction. So you can apply a 50 Newton force, or like I said, pounds is a measure of force. So you could apply a 50-pound force to something this way and shove it against that wall, or you could apply it this way and shove it against that wall. Mass is different. Mass doesn't have any direction. The units for force. So these are kind of crazy. So the units for force are units of mass times units of length divided by units of time squared. We're going to use force all the time, and that's so cumbersome to work with. We're just going to give the SI units of force its own name. So the SI units of force, following this definition, are kilogram, meters per second squared. But we're going to give that the name Newton. And we'll abbreviate it with a capital N. And these are all the forces that we're going to deal with in this class. So let's say these are all the force types we'll see in this class. The first one is the weight force. And that is the force that's applied to an object by gravity. And the second is a category called contact forces. And everything that we see that isn't weight is going to be a contact force. And we're going to divide these contact forces up into 3 categories. I'm going to call it a pushing contact, a pulling contact, and in parentheses, I'm going to put cable here because whenever I talk about a pulling contact, it's in a case where you could replace whatever contact is happening with some kind of string or rope or cable. I'm going to just call it a cable. Okay? So in a way, we're going to use that as a way to differentiate between pushing forces and pulling forces. If you could replace the contact with a string and the system would behave about the same, then that's a pulling force. And then the third one is friction force. Okay, so there are 4 of these total that we're going to have to learn how to deal with. The weight and then those 3. There actually are some other ways that forces can be generated. They're just not going to come up in our problems. But you'll see all those if you take Physics 2. And those are things like electrical attraction, repulsion, or magnetism. But we're just not going to talk about those this semester. Okay, and here is what we're heading towards with this, getting used to using, this is, so Newton's second law. This is kind of our final destination. With particle kinetics. And this is the most important equation in this class. And you've probably sometime or another heard people sort of refer to Newton's second law. Newton's second law is the one that says F equals ma. The way that we're going to think of it is the net force acting on an object, the net force vector, is equal to the mass of the object times the acceleration of the object's center of mass. And that acceleration is also a vector. Okay, so let me be specific about what these things mean. So F net is the sum of all force vectors acting on a chosen object. M is the mass of the chosen object. And ACOM is the acceleration vector of the chosen object's center of mass. And remember, as I say this, the center of mass, because we're not really going to talk about the object's center of mass very often. But it's kind of always in there because remember that when we treat something like a particle, we're treating it like it only exists at its center of mass. So the center of mass is the only place a particle exists. Okay, so now we're going to use what we know so far. We're sort of going to go back like we're early scientists trying to figure this stuff out. And we're going to try to figure out what we can about the weight force. What is the force that gravity applies to objects? So now we're going to use Newton's second law. And I'm going to, when I write Newton's second law, I'm going to abbreviate this as N2L. Along with an object in projectile motion, to calculate the weight force gravity applies to objects. Okay, so that's what we're going to do now. So think of first, think of a 1 kilogram object in projectile motion or free fall. Okay. We know that its mass is 1 kilogram. If it's in free fall, do we know what its acceleration is? Yeah. So we know from just observations and stuff at this point that everything in free fall or projectile motion has a downward acceleration of 9.81 meters per second squared. So the acceleration vector is 9.81 meters per second squared down. Okay. Or we could write this as 0, negative 9.81 for a coordinate system with the y-axis pointing up. Okay. Well, something that's in free fall, the only force acting on it, and you could think through those 4 different types of forces, you know. There's a weight force acting on something in free fall. There's nothing is making contact with the object. It's just alone in space falling, right? So there's none of these contact forces on it. So in free fall, weight is the only force on the body. So let's put these all together into Newton's second law. Okay. And we get that the weight force, I'll call it Fw as a vector, is equal to the mass, 1 kilogram, times the acceleration, which is 0, negative 9.81. And if you multiply the 1 by this vector, you get a force vector that's equal to 0 for x, negative 9.81 for y, and you have units of newtons. Okay, so gravity to this 1 kilogram object applied a force of 9.81 newtons downward. Okay? What do you think? Do you think that's going to be the force that gravity applies to every object, or it's going to change depending on the mass? It's going to change. Yep, it is going to change. So let's do the same thing. You know, that was a 1 kilogram object. Now let's do the same thing with a 100 kilogram object. So the weight force is equal to, the mass this time is 100. What's the acceleration of a 100 kilogram object in free fall? It's exactly the same, yeah, right. So this is 0, negative 9.81. And so we get a weight force vector of 0, negative 981 newtons. And so now let's do it for a general mass. So now a mass m in free fall. And you get that the weight force is equal to m times the acceleration, which is 0, negative 9.81. We're just using the fact that no matter what the mass is, that free fall acceleration is the same. We could also write this as m times 0, negative g. I've brought that constant g up before. And what you get is a force vector of 0, negative mg for the weight force. Okay? So,
I do not understand that.
well, instead of 1 or 100 or 1,000 or whatever, I just used, I replaced 9.81, we've given the name G before. That's just a name. You could call it Gary or whatever, but we call it G, you know. And so we're just multiplying this unknown mass m by this constant G. And so this is what we get. Or, you could also write it as 0. The problem is you have to worry about units a little bit. I didn't say what the units of the mass are, but you could also think of this as 0, negative 9.81 m, as long as you keep everything in SI units. That's all G means. I just use G so that if we wanted to do this in pounds and stuff, we could. If we wanted to use it in some crazy units, we could. Okay, so what we found out is an object of mass m is always acted upon by a force mg down. Okay, and that mg, you could think of that as 9.81 m, as long as you're in SI units. Okay, and so that's what's happening in free fall, but gravity doesn't care whether you're in free fall or not. So whether the person's on the ground or in free fall or in an airplane or a car or whatever, this is what gravity is always doing to any object with a mass of m. Okay. So I want to just try to clarify one thing. I think sometimes this seems weird to people since I spent so much time telling you that in free fall, objects with different masses have the exact same acceleration. But now I'm telling you gravity applies different forces to things with different mass. Okay, well, gravity applies different forces to things with different masses, and it does it in exactly such a way that the resulting acceleration stays the same. Okay, so to accelerate an elephant, it takes a much bigger force than to accelerate a feather. But gravity applies a force to the elephant and a force to the feather in exactly such a way that in free fall, their accelerations would be the same. Okay. So any two things in free fall, if you ignore air resistance, their acceleration is the same. But any two things, the forces applied to them by gravity are different if their masses are different. Okay. Okay, so how does a bathroom scale work to measure your weight? Well, let's think of, okay, so here's someone on a bathroom scale. Looks like he has a front butt. Those are supposed to be shorts. And let's say that this person's mass is 100 kilograms. Okay. And let's calculate, so if the person's mass is 100 kilograms, what does that say their weight is? I'm going to call the weight FW. So their weight would be 100 times 9.81, so 981 newtons. Okay. And somehow that bathroom scale, by having a person stand on it, reads a value of 981 newtons. So let's see how that happens. Okay. So think of the forces acting on the man. Okay, there are two forces. The first one is the weight, and that is 981 newtons down. And the second one is a contact force from the scale. A contact force applied by the scale. And I'm going to call that Fs. And we'll just treat that as an unknown vector. Okay? And now let's put this into Newton's second law and calculate what that Fs is. Okay? So Newton's second law says we have a weight of 0, negative 981. Remember that F net in Newton's second law, the force, is just adding up all the forces on the thing that you're choosing to analyze. We're analyzing the man, so there's a downward force applied by gravity. And there's a force applied by the scale. I guess I'll break that up into components. So Fsx and Fsy. Those are the only two forces. And so you add those up, and that's equal to the mass, 100 kilograms, times the acceleration. So what's the acceleration of the man as he stands there? 0. Yep. There's no change in velocity. The velocity stays 0 the whole time, so this is just 0, 0. And now we can break this up into two different equations. You can think of it as like an x equation that says 0 plus Fsx is equal to 0. And a y equation that says negative 981 plus Fsy is equal to 0. This one tells us, if you just do the algebra to find Fsx, it gives us that Fsx is equal to 0. This one, if you do the algebra, what does it give you for Fsy?
Positive 981.
Yep, perfect. Fsy is equal to positive 981. And so in other words, the force vector applied by the scale is 0, 981 newtons. So what the scale can't really measure your weight. It has no way of measuring how hard gravity's pulling on you. But what it can do is measure how hard it's pushing on you. It can measure that force. And it assumes that you're standing on the scale, not touching other stuff. And if that's the case, then the force it's applying to you has the same magnitude as the force of gravity. Okay? Have you seen The Simpsons? Well, it's really old. I haven't watched The Simpsons in a lot of decades, but the one where Homer tries to go on disability by like getting up to 400 pounds or something. And they have the thing where he's like weighing himself and he's disappointed he hasn't gained more weight, but it turns out he's caught on the towel rack, you know? So if you're touching something else and you're not, then there's a third force acting here, then what the scale reads doesn't reflect your weight. And you know that, you know, like if you're standing on a scale and you lean on the sink or something, it's going to say your weight is less, you know. So let's do one more calculation like this. So this time, let's see what happens if you stand on a bathroom scale on an elevator while it's accelerating. You know that feeling like right at first when you start going up or down in an elevator, you feel kind of a feeling in your stomach, and that's the acceleration. And then pretty quickly that acceleration stops and you're just moving with a constant velocity for the rest of the trip, up or down. But for a really short time there, when the acceleration goes from being at rest to having some velocity, it is accelerating. And so let's see what the scale would say in that case. So what would a bathroom scale measure for a 100 kilogram person when the elevator is accelerating down at 2 meters per second squared. Okay, does anyone have a guess? Is this gonna, so when the person's just standing there on the floor, not accelerating. The bathroom scale says a force of 981 newtons. When the elevator is accelerating down, do you think it's going to read more than that, less than that, or the same thing?
Would it be less?
It is less, yep. It is going to be less.
Because you're being pulled up basically like
So, well, let's see. I think the best answer to why just comes from Newton's second law. So let's just do the calculation and see. So it's the same two forces acting. So now we have a situation like this. Okay, and the elevator is accelerating down at 2 meters per second squared. There are two forces acting on the person. It's the same two as before. So that's the weight and the contact from the scale. Newton's second law says the weight force is 0, negative 981. That's the weight force, plus the force from the scale, Fsx, Fsy. Those are all the forces acting on the person, and that's equal to the mass of the person, 100, times the acceleration of the person. What's the acceleration of the person now that the elevator is accelerating down at 2 meters per second squared?
would it be negative 2 meters per second?
Right. So it's going to be 0 for x and then negative 2 for y. And I'm going to break this up into two separate equations. The x equation says 0 plus Fsx is equal to 100 times 0, so 0. And this tells us that Fsx is equal to 0. So that's not a surprise. There's no side-to-side stuff happening. And now we'll go to the y one. And it says negative 981 plus Fsy is equal to 100 times negative 2. So that's negative 200. And so this time Fsy is equal to positive 781. And so the force applied to the person by the scale is 0.781 newtons. So the scale applies a smaller force. Then once the elevator gets to its, I guess, cruising speed or whatever, the speed that it's going to stay at for the rest of the 5 floors you're riding or whatever, that force will go back to 981. It's only going to be different while the elevator is accelerating. Okay, anyone have any questions about that? I think I might have 1 or 2 problems I can give you. And then on Thursday, we'll get into enough that I can give you like a more normal assignment. Okay, that's all.